lecture on Wednesday?
Yeah, we are. So I wonder if it's getting ready for going to our celebration, but the rage is in the wind. Though I will not be here Monday after Thanksgiving. So what I'd like to propose, depending on what your schedules are like with final exams, is that we use finals week to have a final 2 lectures to finish up wherever we are. Do people have conflicts, do you know, at this time with your finals?
We have one Wednesday.
You do? Yeah, okay. But not on Monday, after finals week. Well, we'll see. I'll let you. I'll query you guys, and we'll see what we might do for making up those lectures. All right. Very good. So, last time we were talking about so-called quasi-classical states of quantized electromagnetic field, also known as coherent states. And formally, we can write those coherent states for an arbitrary number of modes of the field as the displacement operator, phase-space displacement operator, acting on the vacuum. Okay? And each mode is, there is a eigenvalue alpha for that mode. This K is just a generic label for however we are labeling the modes. And if I look at these modes, they are eigenvalues of, they're eigenvectors of the annihilation operator for any mode K with eigenvalue alpha. Okay. Importantly, the coherent states are such that it's a product state, a tensor product of coherent states for each mode, no matter how I write the modes, no matter what set of modes I take. And that's a very important property of these coherent states. It's what, in some sense, relates them to classicality in photo detection. Because if you remember our fundamental assumption in thinking about a semi-classical theory of photo detection is that the photoelectric events were uncorrelated from one another. And that gave us the Poisson distribution. These states, fully quantum mechanical states of the quantum electromagnetic fields, have that property, no matter what the modes are. Now, we also showed last lecture how if I started in the vacuum, the electromagnetic vacuum, and then were to turn on an interaction of the field with matter in such a way that I treated the current as a classical parameter, as a classical field, not as a quantum mechanical current. We'll come back to when that's a reasonable assumption. Then, under that assumption, then we can look at what the time evolution operator is, for example, in the interaction picture, and it's nothing more than the displacement operator. And thus, what we saw is that classical currents radiate coherent states. Coherent states are the fields that arise when we can treat the current that radiates classically. All right? Interesting. Now, I just want to say maybe one more word about that. I can also, it's useful to look at this in the Heisenberg picture as well, just as a little aside here. So let me write the total Hamiltonian. I have the Hamiltonian for the field plus the interaction, okay? Where I'm treating this interaction here in terms of this classical current, just like before, okay? So, so this is the sum over all the modes. Plus this thing that we wrote over here. Right? Here's my interaction Hamiltonian. Okay, so now, if I want to look in the Heisenberg picture, I can ask, how does this operator evolve as a function of time? So what is the answer to that? How do I calculate that in the Heisenberg picture? I take the commutator, right? So this is minus I over h bar, the commutator with the Hamiltonian. The first term is this. And the second term, I'll put all the bells and whistles on, is right? You agree with that? Because that just came from the commutator with this term over here. Right? Picks off that term. Okay, so now I ask you, what is the formal solution to this differential equation?
It's the thing that you said we have to know.
Right. There's lots of things I told you have to know. This is one of them. You should be able to look at this differential equation. You should be able to just look at it and know what the solution is. And what is it?
It's A with the harmonic exponential and then an integral of that stuff.
Right. So I have the free evolution. That would be there if there were no source term. And then I have to, you have the Green's function, which is trivial for this linear problem, 0 to t dt prime to the There's a star problem, but can't solve it here, so I'm going to ignore it for the moment. But there's a complex conjugate problem. So, what can we say about this solution? Well, this here, this is what we call the vacuum term. And this is the source term. But what I see here is that this is just equal to in other words, the solution here, the effect of the radiated field is just to displace this by an amount alpha that depends on the source. Now I have some problem with the complex conjugate here, and I don't know where the hell I screwed that up, but I'm not going to worry about it. And you shouldn't either, because that's not the main point here. The main point is that we can see this very simply, that the effect of this classical force is just to displace the system by an amount that is related to the classical solution. I mean, that's a problem you should have solved in basic quantum mechanics in thinking about the simple harmonic oscillator when I have a classical force. So, if I just think about a simple harmonic oscillator and I say, what is the interaction if I think about a classical force? Well, I can write that as the position of the so that is the effective potential associated with a classical force. And if I start in the ground state of the simple harmonic oscillator, and I apply this interaction Hamiltonian, do you know what the solution is? Did you ever solve that problem? Get your quantum mechanics teachers in trouble.
Is it, you can complete the square?
You can. There's lots of different ways you can solve it mathematically. But what is the solution? So I ask you, I start at time t equals 0 in the ground state of the harmonic oscillator. And I want to know, what is the wave function at a later time? Do you know what the answer to that is, given this interaction Hamiltonian? What would you guess?
It's shifted to the equilibrium point.
But this could be it's true if that was a constant force, but now I'm allowing myself to have a time-dependent force driving oscillator.
You do your trick that you did here.
Yeah, it's the same thing, right? And what this is going to be is a coherent state. In other words, if I start a particle in a well and it oscillates in some way as a classical particle in the well, driven with the force, then what I have is a Gaussian wave packet that oscillates in the well, whose center follows the classical trajectory, and whose uncertainty is the minimum uncertainty at all times. You should solve that problem if you've never solved that problem. This is just the same thing. If I have, now what makes this importantly is that this is linear in x or p. So that this only depended on a or a dagger. So that when I exponentiate it, I'm just going to get something that displaces along x or p, or some combination of x and p. So the fact that this is linear is what made this whole thing quasi-classical. We'll come back to that, the important role of linear versus nonlinear forces, and what role that has in classical versus non-classical life. All right. Very good. So, now we come to our main event. This pen isn't so great, so I'll switch. So what we want to now talk about is the general theory of classical versus non-classical light. I'm going to move forward on this. This is what's going to take us through the remainder of the semester. And there are a variety of things that we think about when we think about the nature of light and what we see. We have aspects of coherence, interference. So of course, as we introduce the semester, the whole subject of quantum optics is really about this, the theory of quantum coherence. And it plays a central role. That's why these things are called coherent states, by the way. We'll come back to that very soon. In distinguishing the kind of interference effects that are associated with classical waves and those interference effects that are non-classical. And then we have aspects of stochasticity. Randomness. Right? The corpuscular nature of events that we see, and to what degree those random events, as we saw in thinking about the photoelectric effect, must be thought about in relation to the non-classical nature of the field, and which are not. Okay? So let's first talk about this point. So this notion of randomness, we have what we've talked about in terms of random photoionization, which was the way in which we ultimately thought about as counting photons, although whether we really had to think about those discrete events in terms of quanta of light or not was questionable. But then we also have something about the random field itself. Now that random nature of the field can be thought about as associated with quantum uncertainty in the field if we are not in eigenstates of something that we would say is a field eigenstate. But there are other ways we can have random field. And in particular, we can think about, when thinking about random fields, we need to, in order to distinguish classical versus non-classical light, we need to think about classical statistical optics, something we began the semester with and we're going to tie together now. So in what way, why should we think about optical fields, or generally electromagnetic fields, as random variables? Classically, in a way that's distinguished from the quantum uncertainty. Well, we just described here that coherent states, which are the quasi-classical states, arose from a classical current. But suppose that my classical current is not deterministic. Suppose I have random current. For example, I guess there's some current flowing in these LEDs, and it's undergoing collisions with impurities and so forth. So we can have, if we have a classical stochastic current, then we have random fields in the classical sense. And we want to be able to distinguish the fluctuations that arise just due to the fact that there is a local hidden variable missing from our description of the current from true quantum uncertainty. Not just because we want to do that, because that will have important impact as to the power, the quantum mechanical power of those states of light to do things that are useful and interesting. So as we studied early on, and you wondered why the heck we did this, well now you know why. We looked at things, for example, we thought about, for example, collision broadening, right? Remember that? Where we thought about a bunch of Lorentz oscillators but that are undergoing collisions in a random way. And as a simple model of that, we said, oh yeah, so if I looked at the radiated field that's radiated by this oscillator, which is oscillating with some basic frequency omega naught, I might have a particular electric field that was, oh, I got a collision and I got some kick, and then I went through and oh, I got a collision, and then I went over here. Oops, I got a collision. These collisions happen at some average rate with some fluctuations between them. So this was our picture of a finite wave train that all of a sudden gets a phase kick, where the phase kicks were discussed, where we studied this in the context of, for example, a kinetic theory of gases, as we studied in the homework, right? And this thing had a spectral density, right? So So in this kind of problem, we thought about, now we treat the electric field at some position in time as a random variable. If I want, I can think about decomposing this into a set of modes in our usual way. With some case I can think about these amplitudes as random variables. In this case, this is one way of thinking about it as a countable set of random variables as opposed to a probability distribution over functions. Right? So if I wanted to, for example, say what is the average electric field, I would integrate over a probability distribution like that. That's what, under this statistical model given some probability distribution over whatever those amplitudes are, and that probability distribution is the kind of thing we studied earlier in the semester, right? In fact, for the case of the collision broadened, if I renormalize these with factoring out the characteristic units and now think about these as random complex amplitudes alpha, okay, that's just taking out the square root of 2 pi, h bar omega, and all of that, because I could have written that over here, factor that out. Then I can ask, what is, for the collision broadened case, do you remember what this is? Good guess. There's lots. Yeah, that's another good guess. Yeah, it's Gaussian. The amplitudes were Gaussian. Remember the quantum random walk that underwent, these phasors underwent a quantum random walk, right? Yeah, well, we do homework and you say, I just got to get the score. What the hell did I do that for? Well, this is why. And so this was equal to and for a whole collection of these guys, I just had the product uncorrelated. Right? This is Gaussian. Right. So if I was interested in thinking about what is, there's a kind of correlation time, a coherence time associated with this kind of wave train, which says something about the average time between collisions. Right? I mean, it's not, they don't go at the perfect time, but there's a kind of average time between collisions. In the collision broadening, we had mean free time was some collision time tau c, if you remember. Right? So, how would I measure that? Well, one way to measure that is in an interferometer, because the phase relation between the electric field at one time and a later will be strongly correlated if the time delay between the two arms of the interferometer is sufficiently short compared to this collision time. Once that time is sufficiently, if the time difference is sufficiently big compared to this, then we don't expect to see correlation. I should say before I do that, I remind you that typically the way in which we measure this is not through this kind of ensemble average, which we could try to approximate by many repeated experiments, but we have the ergodic assumption. And that is a good assumption for this particular case of natural light. And the ergodic assumption involved a couple of different things. We had stationarity. Which is to say, as I wrote here, this probability distribution itself is not a function of time. I could have had something where the probability distribution itself is a function of time. But if the probability, if the statistics are not changing with time, then the stationary condition, in this case, implies, for example, So statistics don't change with time. And to be ergodic, that the system evolves as a function of time in such a way that it samples uniformly from the probability distribution so that expectation values can be replaced with time averages. So when we write this expectation value in the context of classical statistical optics, under the ergodic assumption, if the nature of the stochastic fields is assumed to be ergodic, then I can measure this where I time average for a time t much, much bigger than the period of oscillation of the main frequency of the light. Okay? So to remind you how we measure that coherence time, I can think about a two-path interferometer. Our easiest one to draw is the Mach-Zehnder interferometer, even if it's not the easiest one to stabilize in the lab. But we always draw it that way, because what Michael said just looks ugly. So we have a interferometer to measure coherence. All right. So look at our interferometer with these two mirrors, these beam splitters. Change this with some path difference. There's some path length L1. There's some path length L2. We have some input field at this position in time and some output field. So this, I'll call this at R1. In. And this, if these are 50-50 beam splitters, as we have studied, this is going to be equal to 1/2 the input field at Rn at time t1 plus the input field at time t2, where t1 is t minus L1 over c, so the retarded time to go that distance, and the retarded time what it was at that earlier time, right? Make sense? Okay. Now, what we measure, we're going to measure the output is some square law detector, which measures the intensity by averaging the signal over a time that's sufficiently long compared to a few cycles of the oscillation, which is oscillating, at 10 to 15 cycles per second. It doesn't take much time to get a good time average of the signal, right? So what I'm going to measure is the output intensity. Okay. Now the way in which we often do that is when we do that time average, before I write this down, let us recall that I can write the field always as the real part of, I got some polarization vector and a complex amplitude, right? So this is 1/2 this plus 1/2 this, right? That plus its complex amplitude. This is called the complex amplitude. Now, as we also looked at a little bit earlier in the semester, it is sometimes convention to call this part of the field the positive frequency component and this the negative frequency component. Because of the fact that this is a real function, it puts constraints on the Fourier transform. The positive frequency components of the Fourier transform and the negative frequency components are related to one another, right? Because the overall field is real. So this only is related to the parts that over positive frequencies and these guys over negative frequencies. That's why this is called the positive frequency component and this is the negative frequency component. So the intensity I'm going to write now without units. We'll just say that this is equal to where this average is now the time average. And under the ergodic approximation. Okay. So that's what's measured here. Okay. All right. So since I'm fixing this in, I'm going to leave out the in and the r and just write this as equal to 1/4 expected value of E of T1 plus E of T2 negative frequency component, positive frequency component. Where I'm just putting a shorthand here where I'm leaving out the in and I'm leaving out the position because it's fixed, okay? So this is just a shorthand for this and vice versa. You okay with that? I'm also ignoring the vector nature of the field. I can put all that in, but it's irrelevant for the main point we're trying to get at. So just think about it. I put on a polarizer, it's linearly polarized. I'm forgetting about the polarization of the field. So this is equal to 1/4 All right, so I'm just writing out with all terms z in my interferometry, right? Just writing out all those 4 terms. Now we go with the ergodic stationary assumption that because this is stationary, these 2 time correlation functions only depend on the time differences. Right? So this is equal to the input intensity, right, which is, because it only depends on the time differences, which is the difference between these 2 times. It doesn't matter as long as they're equal times, it's the same thing. This is also the input intensity. This is equal to that from the stationary statistics assumption, and this is equal to this from the stationary statistics assumption. All right, with that said, we can now, by the way, let me define a function I'm going to call G1, capital G1, as a function of R1, T1, R2, T2, is generally defined as the expectation value of E minus R1, T1. This is a correlation function. Now, because we are looking at correlations always in terms of the field at 2 different times at the same position, and we do that through the retarded time, often when we're talking about temporal coherence rather than spatial coherence, we will just think about, we will not write the position dependent and write them just in terms of their time dependence. And in particular for stationarity, we often just write this as a function of one argument, tau, which we'll write as the expectation value of E minus and tau, E plus and 0. So we have this thing called capital G1. All right, so my interferometer, my Mach-Zehnder interferometer, measures this output intensity. It equals 1/2 G1 at 0 plus twice the real part of G1 of tau where tau is defined to be L2 minus L1 over C. I'm sorry, the 2 I factored out over here. So what did I do? I wrote this as G1 of 0, and this is G1 of 0, right? Because it's the same time. And I have 2 of them. So I factored out the factor of 2. And then I have this plus its complex conjugate. That plus its complex conjugate is equal to twice the real part, which is this. And this is nothing more than the intensity. So, what I have is that this is equal to the input intensity over 2, 1 plus the real part of G1 of tau over G1 of 0. Okay. And we write this, it's notation galore here, as 1 plus the real part of little g1 of tau. Little g1 of tau is defined as big g1 of tau divided by g1 at 0. For reasons that will become clearer soon. Okay, so this is the output intensity. Now, how am I going to find G1 of tau? Big or little? Well, now I have to dig up something else from the homework of yesteryear, also known as September, which is what is the relationship, G1 of tau here, let's look at it over here, is this. It's what we sometimes call an autocorrelation function. We're correlating the field with itself at 2 different times. In this case, the field with its conjugate at 2 different times. How do I find what that is, given this statistical field, the field that is fluctuating in this way?
Use a Wiener or something.
Wiener Chin-Chin. Wiener Chin-Chin, which we cannot spell, but we can sort of say. The Wiener Chin-Chin theorem says what? Why did he make us do that stuff? This is why. The Wiener Chin-Chin theorem says that the autocorrelation function is just the Fourier transform of the spectral density. The spectral density says if I look at the Fourier transform of these guys at 2 different, it has some strength, which is the spectral density. Right? Remember that? And for a collision broadened source, here's your cue, David. What is the spectral density of this fluctuating field?
Sophia Lorenzia.
Thank you very much. It was the Lorentzian, right? So if I looked at the spectral density for the case of the collision broaden, which we solved, we saw that, well, you know, the Lorentz oscillator has some mean frequency, and then there were these Lorentzians around them. With the had in this case, we have this Lorentzian centered at those are Lorentzians that have a width like gamma, which is 1 over. Okay, so now, what is the inverse Fourier transform of this? Actually, this is not quite right. It's only over the positive frequency part here. There. So how am I going to do that inverse Fourier transform? Well, I only have to do the inverse Fourier transform over this section. And what is the inverse Fourier transform of a Lorentzian? It's a decaying exponential, which is decay rate given by tau, right? So I can write this spectral density as this Lorentzian convolved with two delta functions. One centered at omega naught and the other centered at minus omega naught. This is the convolution. So, from that, I can do the inverse Fourier transform of this. And what it's going to be is, let's call that sine tilde, the inverse Fourier transform of gamma e to the minus I omega naught tau. Where gamma of tau is the inverse Fourier transform of this guy, which is a decaying exponential. All right, so that's not quite right. It's not quite right. Let me come back over here. I lost, when I wrote this, the actual energy density. This is per unit intensity. This is really multiplied of that. Now that's right. That's the actual, I mean, it has to depend on the intensity, and that's how it does. I normalized it in my head, but that's not right. That's the actual spectral intensity. So this is equal to, still equal to this, but this is equal to this. Now it's correct. However, what this tells me is that little g1 of tau is equal to what? It's equal to gamma of tau. All right, let's put it all together. back down so you can see what we were looking at. We have the output intensity is equal to the input intensity over 2, 1 plus the real part of G1 tau, which equals that. Okay. Let's sketch that. As a function of tau. What I see is the following. And you can sit in the other, and it goes, it's symmetric. I'm not going to try, but it looks exactly reflection symmetric. Okay. So what does this tell me? What I see are interference fringes. However, those fringes have a certain visibility. The depth of the fringe, the difference, the visibility of the fringe, depends on the path length difference or the temporal difference compared to the coherence time, or equivalently, the coherence length of that wave train, right? So when the path length difference is too big, I don't see interference. What I see is half of the intensity comes out one port. But when the distance is sufficiently small, compared to the coherence length of my wave train, then I do see interference. Right? Not surprising at all. But the way that I can measure the interference here, the decay of this visibility tells me something about the coherence time. If my interferometer is more unbalanced compared to the coherence time, I don't see interference. No surprise there. Now, I can understand this we just described completely in terms of classical statistical optics. Right? We treated the field as a classical field that was a random variable, and we made certain assumptions about the correlation functions, and through that we were able to see how the interference fringes would fall off as a function of that imbalance. But how do I think about this in terms of photons? Well, what I can loosely, and we'll come to this in a more precise way, perhaps during this lecture, is to say, from the point of view of photons, what I have is my beam is a collection, is a stream of photons. And each of those photons is like a wave packet because it has a spectral density, right? So we have photon wave packets. I have these kind of whole stream of these kinds of guys, lots and lots of these photons that are streaming along. Each one has an extent that's on the order of tau c, which is related to the inverse of the width of the spectral density. Each of these photon wave packets enters the interferometer, and the probability amplitude gets split, right? And if the imbalance in the length of these arms is longer than the size or the extent of that photon wave packet, well then the photon cannot interfere with itself. And in this interferometer, the interference is associated with each photon interferes only with itself and not with another photon. So when the imbalance is too big, then in this interferometer, we don't see that. Yeah, right.
So the length of a photon depends on the coherence of the source that it comes from?
That's correct. That's correct. So if I have that could be, it's a little bit complicated here because this is a cartoon that one should take with a certain grain of salt, because the source that I'm talking about here, as we'll discuss in detail soon, is not a deterministic source. And thus, the state of the field is not a pure state. It is a density matrix that is a statistical mixture of different pure states, because I don't know what the source was that made that, right? That's what the classical statistical optics is. So we complete that formally. Quantum mechanics does it all. Anything you want, quantum mechanics knows how to calculate a probability, but we've got to treat the state of the field in that case as a mixed state. So this is really something more, not about the probability amplitude, but something more about the probabilities of numbers of photons. It's a little complicated, we'll get to it. But the essential point you make is right and correct, that the source determines something about the coherence length. And the spectral density of the source, if it's a broader band source, it's a narrower photon. The coherence length will be shorter. Yeah?
So we still have something like a thermal gas source.
That's right. That's right. That is producing this kind of what we would call natural light. Okay. All right. Now, I just want to introduce. So now, fine. This is how one measures generally coherence times or coherence lengths of the field by looking at interference between the amplitudes. Now the problem with that in practice is if the coherence time is very, 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 very long, then it would be very hard to make a stable interferometer with a very big unbalanced arms that would be able to see this, right? And in particular, there was a couple of radio astronomers named Hanbury Brown and Twiss. Now, Hanbury Brown is one person. He doesn't hyphenate his name, but he's one person. And Twiss is another guy. They were radio astronomers in the 1950s. They probably were. They were interested not, in their turn, in the temporal coherence, but spatial coherence. They were interested in measuring the angular size of stars, or whether a point of light that you saw in the sky was from two stars or one. If they were from two different stars, they would be incoherent sources. And there is something called a Michelson stellar interferometer, which would look at light coming from 2 points, which would have in the distance, in the far field, with 2 different Ks, reflect them onto some, have some kind of mirror that would reflect these guys we have in 2 different sources, and reflect these guys onto some lenses here, and you'd see some fringes. And the coherence area of these fringes was related to the question of spatial coherence, as opposed to temporal coherence. The Mach-Zehnder interferometer asks, is the electric field coherent with itself at 2 different times at the same point in space? Spatial coherence asks, at the same time, do these 2 different sources, right? This is kind of irrelevant, but it's a little piece of the history. The problem with the stellar interferometer, and excuse my horrible drawing, don't really care. The point of it is the following, that you had to see these tiny angular distances between K1 and K2 required you to have huge unbalanced arms of the stellar interferometer, right? Because this is the Fourier inverse relation. The smaller the difference you want to make, the bigger you need to make the interferometer. It was a very unstable beast. And so they said, screw that. What if I just do the following? Instead of trying to interfere the 2 light beams, what I'm going to have is 2 antennae, radio antennas, VLA like these, where light can come in from these 2 different directions, K1 and K2. And then I'm just going to, instead of correlate, I'm going to take the current that comes out of my antenna. I'm going to time delay it by some amount and measure the correlation of the intensity at these 2 different, well, let me just say it this way. In this case, they're looking at, so now I have some distance, d. So this is a spatial coherence. So what they did is they said, let's just take the current And instead of looking at this as a function of the arm distance between the two arms, I'm just going to absorb the light, get a photocurrent, and correlate the current. This is as we will see, an intensity correlation function. As opposed to the beast we just looked at, which is a field-field correlation function, correlating the electric field with itself at two different space-time points. This was, as we'll describe in more detail, a beast that basically correlates the intensity with itself, in this case at two different points in space. Now, to compare to our Mach sender, it's easier, and ultimately what the first experiments that Hanbury, Brown, and Twiss did to test this idea is, let's think about this from the point of view of temporal coherence. Okay. So let's imagine the following thing. I have a lamp, also known as a light bulb. Okay. And the light comes out of this, and I'm going to put it on what was at that time called a half-silvered mirror, now we call a beam splitter. Okay. And I'm going to have two detectors on either side of the beam splitter, symmetrically distanced from the beam splitter. Okay. It gets a photocurrent, and we're going to time delay this, and we're going to mix them together to look at the product of these and time averaging, also known as the distance average.
I1 and I2.
So there are two different intensities. One is time delayed from another, so that's as a function of tau. Okay. Now, what do we expect to see? In this case, there's no two arms of the interferometer. It just is one beam splitter. And we're just taking the light. Some of that light is transmitted and some of it is reflected. We get a photocurrent. Classically, the photocurrent is going to be, well, let me call the photocurrent measurement a function of time. It's going to be some sensitivity of the photodetector proportional to the intensity plus shot noise. And so if I correlate the photocurrent at two different times, well, that's the same thing as correlating what the stochastic intensity is at two different times, because the shot noise is uncorrelated from the intensity. So just correlating the photocurrents with one another at two different times is equivalent to correlating what was the intensity that hit those photodetectors at two different times. All right. So what do we expect? Well, I can write that intensity correlation function, or photocurrent correlation function. I'll write it in the following way. So I can always write that stochastic variable as whatever the mean value is plus some fluctuation around the mean at that time. This then is equal to right? Okay, let's just complete this one last thought. So my intensity correlation function, to the degree to which this thing is ergodic, the average intensity is not changing as a function of time. The intensity is changing as a function of time, but the average is not changing, plus the correlation in the fluctuations. So, what do you expect to see from a natural light source in this system? What would we look like as a function of the time delay, tau, in that Hanbury-Brown Twiss intensity correlator? What do you expect to see? Well, the intensity, if I were to ask, what is the intensity doing as a function of time instantaneously? If I had a fast photodetector, what would I see? Well, the intensity is going to be fluctuating all over the place. Right? There's some mean intensity, time averaged. And you remember from your homework what the probability of seeing a certain intensity is from our collision problem source? Right? Give you all this stuff. This guy, for this probability distribution, we have that the fluctuations in the intensity, so say delta I squared to I squared. Now, how long the intensity stays kind of constant is related to the coherence time. The intensity on my photodetector is fluctuating. It's not a constant. If whatever intensity is hitting my eyeball right now is not the same. It's changing as a function of time. But it's kind of constant, correlated with itself over some time scale, which is the correlation time. So now I ask you to conclude the following. What do you expect this correlation function to do as a function of tau?
Diminish?
It should diminish. When it's at time t equals 0, well, this is equal to this, right? So if I look at this when tau is 0, well, that's going to be equal to the average of I squared, which is twice the average of I squared, what we just wrote down there, right? Because this fluctuation at time t equals 0 is equal to the average of I squared. But what happens when tau is much, much bigger than tau c? What do you expect this to be? We expect this to be 0. There's no correlation in the fluctuation with itself, and we expect this to equal I squared. So, what would I expect to see? If I look at this guy as a function of time, I should see the following. For short times, the intensity is highly correlated with itself, and the correlation of I with I is equal to twice the mean I. But for long times, there's no correlation. And it's just, so I expect to see something that looks like this. In fact, as we will see next time, this is equal to I squared 1 plus e to the minus 2 tau over tau c. And so I see the coherence time in terms of the intensity correlations in these detectors. But now the paradox. What the heck? We just said that this was related to this effect that we saw, the interference of the photon with itself going through two paths. There's no two paths that any one photon goes through in this detector. One of the photons might go here, one of the photons might go here. But no one photon is interfering with itself. This drove people nuts in 1958. And people said Hanbury, Brown, and Twiss were wrong. And they didn't give them the funding to do their experiments, so they moved to Australia, where they did their stellar interferometry, and they worked. And they did this experiment. And it drove people nuts. And it was the explanation of what's going on in the Hanbury, Brown, Twiss effect is what led to the birth of quantum optics. And the father of quantum optics was a guy who passed away 1 year ago, who definitively explained it all, and is the father of quantum optics. And we'll describe that